The independent variable is the...
You've got a 50% chance of getting this right.
The mass?
What did you say? The mass is the what?
The independent variable.
And why would it be the independent variable?
I don't know, Mr. Funny Cook, I'm confused.
Right, you've got an, let's just allow, Quanda's trying to come in. You've got an opportunity to phone a friend. Who would you like to nominate in the class to help you?
Amy.
Amy, where are you, Amy? Okay. Amy, you've been nominated. Help a friend.
Yeah.
Have you heard the question?
Yeah, I did hear the question. I think the independent variable will be the weight.
No, Naledi was right. The independent variable is the mass.
Oh.
My follow-up question was why is the mass the independent variable?
Because
Hannah wants to help. Sorry, not Hannah. Sarah wants to help you, and Apilele wants to help you. But let's give it a go, Amy. Quick.
So the mass is the one with the triple beam balance, right?
That's right.
I think that's the independent variable because it doesn't change. The mass can't change.
Okay, close. I'm going to just jump over. Thank you, Amy. I'm going to mute you and go over to Sarah. Let's Sarah.
The independent variable is the mass because you're changing the mass for each thing, and then that determines the weight.
Spot on. Thank you. So, girls, you heard that the mass is the independent variable because basically you have control over that. You decide what the mass is of the object, and as a result of the mass, you're actually measuring the value of the weight. Okay, so the weight is sort of an unknown for you, and you determine the weight through that. Thank you, Sarah. Well done. So I'm going back to sharing my screen again. So here are some values that I've filled in. Normally what we do in the lab is get you to determine the weight with the spring balance. But for now, that's what we do. So the dependent variable is the weight, and the independent variable is the mass. And that's important to identify in an experiment because you need to determine which of the two axes those variables will be placed. So the dependent variable, as you know, will go on the y-axis, which is vertical, and independent will go on the x. Now, a couple of things about the graph. Before you even start plotting points, there are about probably 4 or 5 marks that you can bank very easily by getting this right. Firstly, you need a heading, okay? And you can put a fancy heading if you like. We're going to go graph of weight versus mass. Now, you might ask yourself, why did you put weight first and not mass? Because typically in physical science, we would like to see the value on the y-axis be written first. So this is typically y versus x. If we're not plotting y, we're plotting weight and mass, okay? So you get 1 mark for putting the heading down, something which you girls forgot on the previous graph. Not all of you, but a few of you, you tend to forget that. Then the second thing we want to do, because we know we're going to put mass down on the horizontal axis, we want to put the mass down. You get a mark for that. And you need to put the unit in. kg, small k, capital G. And on the vertical axis, if I can get my pen, we want to write the weight. And that's in newtons, capital N. Our bank already, depending on how generous the examiner is, 1 mark for the heading. Sometimes they give you 2 marks for writing the label and the unit, and the same there. So that's possibly 5 marks in total. Then we want to plot, and I've just copied my table down so that I don't have to keep paging to the top. We want to plot, this is mass here, and this is weight. Okay, so let's first deal with maths. 0.5, 1, 1.52. I want to use as much of my scale as I possibly can, of my page rather. So I'm going to go with these lines. That's 0.5, that's 1, that's 1.5, and that's 2. And I'm going to put the 0 in. Okay. The weight goes from 0 all the way to 19.6. So I'm going to try and use as much of the page as I can. And I need a scale that's going to be nice and even. So if I were to look at these major blocks here, I need to go all the way up to possibly 20. So that could be nice in units of 5, 10, 15, 20. So every 2 little blocks here would represent 1 Newton. So the 0, 0 is easy to plot. Oh, by the way, also need a 0 on that scale. 0, 0. Put a point down, little circle around it. 0.5 and 4,9. So the mass is 0.5 up on that vertical line, and 4,9 would be, so remember, 1 every 2 blocks is 1. So that there would be 4, 4,5, 4,9 is pretty close to 5. About there. Next value, 1 and 9,8. So 1 and 9,8. Again, that will be 9, 9.5, 9.8. Pretty close to the top. Next one, 1,5 and 14,7. 1,5, that will be 11, 12, 13, 14,5,7, so in the middle there. And mass of 2 and 19,6. So that's 19,5, just above that line. Okay. The reason why we put a circle around it is when you draw your straight line, it's possibly going to be that we can't see the point. So that's why we have the circle around it. So then what we want to try and include is a straight line. And I'm going to take my graph and as best as possible. And by the way, a little trick to get it to move so accurately, I'm holding down the Alt button, ALT on my keyboard, and working with my mouse to get it pretty accurate. And I'm extending my line just beyond that. And look at that, my points were beautifully plotted. Okay, and I get a straight line graph, like it says in number 4 there. Your graph should be a straight line. Even though 0, 0 was not essentially one of the values, you need to extend your graph to pass through 0. And that's because when the mass is 0, the weight is 0. Now, the next question is asking you to work out the gradient. But I want to pause just here. I'm going to stop sharing. And I want to check with you if you have any questions on the drawing of the graph. So you can put your hand up, raised hand. Okay, thumbs up if we're all okay. One question coming through, but lots of thumbs up. It's Caitlin who has a question. Caitlin, you are on air.
So I just wanted to ask, so like, I know you're not doing this like you're doing it properly, but if we had to do it for marks, wouldn't we have to use all the space of the graph on the sides and the bottom for our numbers?
No.
So like, wouldn't we have to go past 20?
No, you don't. It will depend on the actual points. But the guideline we give is that you must definitely use more than half of the graph paper. So we don't want to see a graph squeeze into a corner. But certainly you can extend the graph. The line that I've drawn, you can extend. You can extend it as far as you like, really. But what I've drawn is meant to represent a perfect example of what the graph should look like. Okay. The only thing I'm going to touch on now is what I call the line of best fit. All right. Great. Thank you, girls.
Okay,
thank you. Sorry. I'll go back to full screen. And so just one other thing I want to point out is sometimes you'll find that you have a point that doesn't actually, or you might have points, for example, that don't quite lie on the graph. And that's okay. You might have points, if we add extra points that look like that. It's okay if it doesn't lie on the graph. Don't try and force things to be on the straight line graph, right? That straight line that you've drawn is what we call a line of best fit. As long as you can try and sort of get that line so that you have an equal number of points on either side of the line, then you are doing well. Okay, but for now, that's our graph that we've got. And that's okay. So I just want to remind you again, all graphs must have a heading, a label at the top. Your axes must be labeled with the unit in brackets. And then you need to choose a scale that will try and get your graph, or if I look at the horizontal scale that we've got over here, try and get more than half of that horizontal line being used, and the same on the vertical axis. Okay, and I think what I've done is really the best scale that will allow you to use more than half of the graph. Good. The gradient of the graph is a question I'm going to leave for you to do for prep. Okay, and again, I want to check where you guys are at in terms of mathematics and if you can calculate the gradient of that graph. So there is a video that I'll put up as well to help you through that. So when I look at this graph, what is the conclusion that I can have? If it's a straight line and it passes through the origin, there's a couple of things I can say in terms of the conclusion. Right? That the weight, firstly, is directly proportional to the mass. You can say that in other ways, that as the mass increases, the weight increases. But scientifically, that's the correct terminology. When you have a straight line graph passing through the origin, in the two variables that you are plotting against each other, they will be directly proportional to each other. I see a raised hand. Apelele's got a hand. Let's just find it quickly. Yes, question. I'm listening. Apelele, you there?
Yes,
Yes. Sorry. Come again.
you know what? How you said the weight is directly proportion in the mass. Can you not say direct relationship? Because that's one of the names we used in one of the graphs last year.
Yes. The relationship part we sort of keep for life sciences, biology. But yes, there is a direct relationship between the two. But mathematically, we're going to start talking about proportionality. So that's why I want to put the emphasis on proportional. But you're quite right. We could also say directly that there's a direct relationship. But mathematically, it's proportional. Okay.
Okay, thank you.
Thank you. I'm going to move on then. You can just mute yourself so that we don't get feedback. I wrote this answer in the wrong place. I think my conclusion was meant to be over there. So I'm just going to do that for now and move on. Okay, so weight then is the force of gravity pulling you towards the Earth, measured in newtons. That's not new to us. On Earth, the gravitational force causes us all to accelerate towards the center of the Earth. That acceleration is called gravitational acceleration. On planet Earth, it's got a value of 9.8 meters per second squared. The gradient that you calculate above, you're going to find that it will have a value of 9.8 meters per second squared. And there was a question in our collaboration space about free fall, and Felix Baumgartner, free fall when the only force acting on the object is the gravitational force. Okay. For weight, we calculate the weight of an object by taking its mass and multiplying it by this value of g, the value of 9.8. Now you'll notice this textbook is using capital W. I previously gave you the symbol F subscript G. the force due to gravity. Mrs. Forrest is using that FG quite a bit, but your textbook uses capital W. So here's the formula to work out the weight of an object, M times G. What is the value of G that we use? 9,8 meters per second squared. I don't want to get into the units just now. We'll deal with that. The important thing is the number 9,8. And I'm going to draw your attention to this little triangle that we can also use. Capital W, M over G. So how do we use this triangle? Well, if you're trying to work out weight, you close up the W, and W would be the M times the G. That's the formula there. If you're wanting to work out the mass, you close up the letter mass with your finger or your hand, and you'll see you've got W over the G. So that's the formula. If you want to work out G, you close up the letter G with your finger or your hand, and you get W over M. Okay, so that's the question that we've got. Just another important couple of points. Obviously, different planets have different gravitational acceleration. That G is also the strength of the gravity on that planet. And there's a couple of things here. The moon, for example, is 6 times smaller than the Earth. So the gravity on the moon is a lot less than the Earth. Jupiter, gravity is about 2.5 times that of the Earth. And we can go through all of the planets. There'll be a table later on that we look at. Okay. So here's another important point. An astronaut's mass will remain the same wherever it is measured. You've got an astronaut here on planet Earth. His mass is a bit small, but it's 1,200 kilograms. Sorry, 120 kilograms. And the weight is approximately 1,200 meters. They've just multiplied it by 10. Should be multiplied by 9,8. Okay, 120 times 9,8. But the astronaut's weight, however, depends on where you measure that weight. Remember, weight is a force. Mass is just the amount of matter. So on Earth will be 1,200 newtons, but on the moon, it will only be 200 newtons. So there you go, 200 newtons on the moon, because the value of G on the moon is very small compared to the Earth. So capital W is M times G. So here are a few examples. I'm going to do some of them, that the rest you will do on your own. Okay, so let's start with a favorite Formula One team in the world, Ferrari, although they haven't been champions for a long time. The mass of this car is given. We want to know what is its weight on Earth. We always will solve these problems with a formula or an equation. W equals M times G. I'll just do my little triangle so that you guys can see M times G. The mass of the car is 1,485. Multiplied by the value of G is 9,8. You get your calculator. And I wish I had my calculator with me right now, but I don't. So we call up calculator app. And there it appears, and we work out 1,485 multiplied by 9.8. We get an answer of 14,553. 14,553. And the answer is B in newtons. How would we mark this? 1 mark. Let's not be as generous with those sorts of ticks. We'll give 1 mark for the formula. Okay. Sometimes the examiner might give 2 marks for what we call the substitution step. You can only get a mark in the final step if you include the unit. Very important. If you leave that capital N out, you will lose the mark at that point. So that's how I want you to tackle the questions on this. And we will look at some of these in a moment. What I want to come to question number 5. Okay. If a car weighed 1,340 newtons, so that's capital W on the moon, what is its mass? So I'm just going to remind you of the triangle. Capital W was M times G. So what are we given in this question? We're given the weight, and we wanting to know what the mass is. If I look at this formula, mass would be equal to capital W over G. So the mass would be 1340. I need to now find the value of G on the moon. On Earth, it's 9,8. But up here in your textbook, they tell us that the value of G on the moon is 1,6. So 1340 divided by 1,6, I get the mass. So for that, I need my calculator. I just need to move this up so that I can get my calculator to see. So this was 1340, and I'm dividing that by 1.6 equals, and we get an answer of 837,5. This was 837,5. What am I working out? The mass, and the mass will be measured in kilograms this time. All right, so mass is in kilograms. And that's how we solve that. Again, just to give an idea of mark allocation, 1 mark, 2 marks of substitution. We only get the final mark if we have the unit. And that's how we deal with that. The rest of the questions, I'm going to let you try. That's question 1 and 5 I've done, and you can see why I've done question 5, because just a different way of manipulating that formula. Okay, so let's jump straight into the next activity, which is quite a simple one to do, but you need a calculator with you to do this. And I'm going to ask you to fill in your mass. I'm going to be ambitious and say, well, at the moment, I'm going to say I'm weighing about 70 kgs. So obviously, the mass on all these planets will remain the same, assuming I don't lose any mass in my travels to each of these planets. And what I need to do is to get a calculator and calculate my weight on each of those planets by using the formula weight is M times G. And so I'll just do a couple of them again so that we can see how we get that. So on planet Earth, for example, 70 multiplied by I can't get this thing down. 70 times 9,8 would be 686. I don't have to put the unit in. Why not? Because this is a table and the unit appears at the top of the table. Let's do one more. Let's take Jupiter, which has got gravitational acceleration of 26,1820. So I will feel quite heavy on Jupiter, a lot heavier than what I do on planet Earth. And you can work out the rest on that as well. And then fairly easy questions that go with that. So that's the weight of an object. And then I think I'm going to stop here just in terms of the magnetic fields, because we do want to split this lesson and we'll start to look at the rest. So I'm going to jump all the way to the top, Control Home, if you didn't know that, and just remind you what you need to do. So you need to look through this again in your own notebook, fill out these values on your own, go ahead and draw the graph, right? I want you to practice that because it's really important for you to practice, because the skill I'm looking for is you being able to work out a scale or a good scale that you can use. There's nothing to work out really, it's just to figure out what's the best scale. You must then calculate the gradient and you must answer the rest of the questions. The conclusion I've actually written up there before. And then on this next activity, I've done question 1 and 5. You must complete the rest. Question 2, question 3, question 4. And then in the last activity, complete the table and answer the questions 1 and 2 that follow. And that's where we'll stop. I'll stop sharing my screen and check if there are any questions. We're all good. Thank you, Caitlin, for that thumbs up. Jasmine, I'm going to put you on the spot. Jazz, here's a question for you. And hopefully the rest of you just question to figure out whether people have been listening very carefully. Jazz, the question is, if I have a mass of 70 kilograms and I travel to the moon, will my mass be more or less or the same as what it is on Earth?
I think less.
Why would it be less? There's always a why. Because the gravity
is different on the moon.
Okay. Now, if you had listened carefully, that was a trick question. Anyone pick up that trick question? Raised hand. Gemma is first. Yes, Gemma. What was the trick about it? What did I ask?
Can you hear me?
Yes, I can.
Okay. The mass would always stay the same. It's the weight that's different.
The mass would always stay the same. It's the weight that's going to change, right? So my question again, I repeat, I said, if I have a mass of 70 kilograms on Earth and I travel to the moon, will my mass on the moon be more, less, or the same as what it is on the Earth? So that's a very good question. Caitlin has a question.
Sorry, so I don't know if you explained this in the last lesson, but I wasn't there because of my sound. But what's the difference between mass and weight?
So mass is the amount of matter an object is made of, right? So all the molecules, the atoms that make up something, that is mass. The weight, weight is the force that the Earth attracts an object. Now, it could be the Earth if you're on the Earth, or it could be the moon. So the weight is the force that you're being pulled towards the center of that planet or that object. So that's what, and that's why weight is a force in newtons. Mass is a value in kilograms. Okay.
Okay. Thank you.
Thank you. Any other questions? We all okay? We all know what we need to do? I was going to plan on jumping ahead to magnets, but I think I'm going to just slow things down a little bit. So it's not a lot of prep. You've got about 13 minutes. You could actually finish it now. I promise that I will be looking through your notebooks. I do have major technical issues at home here with electricity, but yeah, I'll keep pressing on. So I am still on screen or at my computer if you have questions. All thumbs up. Let's see your thumbs up if you're okay. Perfect. I'll match most of you. Some of you trying to find the thumbs up there still. Thank you, girls. Keep pressing on. And after this lesson, enjoy your last lesson for the day and have a good weekend. Oh, you've got Saturday school as well. Blue Saturday tomorrow. Thank you. Meeting ending. You may leave. Goodbye, Apelele. Do you have a question? You still there? Hello?